Hello everyone, this is Sylvia. In the last session, we learned how to manually load data by using a battery degradation dataset, for example, and plot some basic curves. However, manually load data often do not give us the desired results directly, won't allow us to create more colorful plots. So in this session, we will learn how to manually write code to perform tasks to arrive at our desired results, such as we will write codes for the data loading and to create some range visualizations. So by the end of this course, you will be able to produce colorful figures with more detailed information. So let's begin as we did in the last session by opening the MATLAB panel. Place the downloaded battery dataset in this current folder. I strongly recommend that you follow along and practice hands-on. This will significantly improve your coding skills rather than just watching us to do it. Those interested can find the download link for this dataset in the last video, PT5. This dataset is publicly available, so you don't need to worry about access permissions. We need to create a new script where we write our code. While it is also possible to write code directly in the command window, writing it in a script offers significant advantages, especially when working on longer programs. Writing in a script allows you to avoid debugging line by line as you would in the command window. Instead, you can write the entire program, check it for errors, and then execute all at once. First, let's save this script. It will be saved by default in the current folder. Let's save it as PT6, as this is our 6th lesson. Then click Save. It will be automatically saved in MATLAB's executable file format. Let's load this dataset into MATLAB using code. It's very simple. Just specify the root path and append the name of the dataset. Because this dataset has been already placed in the current folder, so currently we do not need to specify its root path, but only give its full name. Then assign the loaded dataset to a variable. Here we called it data for storage this dataset. This makes it convenient for us to process the dataset later, as we can directly reference it by using data. Execute this code by clicking the Run button, the green one. Then return to the main interface. Under the workspace, this window, and you can see a new variable named data. This variable, data, it contains everything from the dataset we just loaded. You can double-click it to open and explore its contents. All the data is stored under the batch variable. If we want to use the data in this dataset, we need to declare it in this way. This is a method for accessing data within an array. For short, we give this variable a new name, batch. Similarly, we can locate the discharge dQdV feature in batch 1, circles 1. To simplify its representation, we can assign it to this variable, dQdV diff. Then we can plot it by creating a figure and visualizing it accordingly by input the plot. Inside the bracket, it should be the simplified variable. Next, let's add an x-axis to this plot. Similarly, we locate the batch 1 VDLIN variable, which represents the voltage during this data collection. Then we call the plot command again, placing this voltage variable in the first argument of the function. Please note, the order of variables is crucial. The first variable represents the x-axis by default, and the second position is left for the y-axis. We will execute the programs in part 2 and part 3 separately. This allows us to observe the difference between the two generated plots. You can see here, the left is the first plot. It uses the nature sample numbers as the x-axis, while for the second one, we successfully added the corresponding voltage values as the x-axis. Now let's add the x labels and the y labels. As you can see, the current plot is quite empty and lacks the proper labels. So to fix this, we add labels to the x-axis by using the x-label commands, and by adding such two lines of code, then selecting and executing them by clicking the right side of your mouse, you'll see that the x-axis and the y-axis are the plot, and they are properly labeled. However, at this point, we have only plotted the dQdV feature for a single circle of this degraded battery. We have not yet obtained this feature across different circles. What we aim to do is to exact and plot this feature across multiple cycles. This could allow us to compare them and observe if there are any distinguishable patterns. So now, let's proceed to plot the features at multiple circles. From what we observed earlier, this battery has about 1000 circles. We'll set the maximum value to 1000 and assign it to a variable num circles. Next, we'll write the for loop, iterating from 1 to this num circles. For each iteration, we will plot a single line corresponding to the dQdV feature about this circle. However, unlike before, we plotted only a single line. Now, if we want to plot multiple lines on the same figure, to achieve this, we need to use the hold-on function to return the existing plots while adding new ones. Finally, we execute this block of code to generate the multiple line plot. And here it is. Extremely cluttered due to the large number of lines, and the color are not predefined. With 1000 lines displayed, it is challenging to identify patterns in the evolution of this feature under different aging conditions. To address this, we will assign a gradient of colors from circle 1 to circle 1000. For instance, at the beginning of the battery circle's life, like the circle 1, we can assign it with a very light color, reversely a darker color for the circle 1000. If there are noticeable patterns related to aging, they will become apparent through this gradual color transition. In part 5 of this code, we first define the color gradient by specifying the colors variable. In this bracket, we input the max value required for this array, which is determined by the num circles. So we assign a num circles to this parameter. The ultimate function in MATLAB is a built-in color map function that generates a gradient of colors. If you are not familiar with it, you can use it as shown here for now. Then we make a small adjustment to the plot command by adding the colors parameter. Specifically, we include a line of code to assign the colors we just defined to the plot. Ensure each line is colored according to this gradient. Additionally, we add a line of code to introduce this color bar. This color bar offers a visual representation of how the feature evolves across the 1 to 1000 circles. It helps us understand the relationship between the color gradient and the corresponding circles. And finally, we execute this block of code. Now, after multiple modifications and the additions to the program, we have finally obtained the vibrant feature evolution plot that we aimed for at the beginning for this presentation. From this plot, we can observe that the dQdV feature does show a certain pattern of evolution as the battery gradually ages. For example, the most noticeable feature is that as the battery ages, the lowest point of the feature shows a gradual upward trend. In the next session, we will learn how to build our own AI model using MATLAB's toolbox. We will use these features to explore whether they can be applied to evaluate battery aging. It's that simple. See you in the next session.